We're going to be discussing rational functions right now. Remember, what we know about rational functions is a fraction that has a variable in the denominator is essentially just a colloquial definition of a rational function. What we know so far about rational functions is trying to find the domain of a rational function after identifying it. And remember, x squared minus 11x plus 28 here, which is the denominator of this, cannot equal 0 for any input of x. So that's what we're going to try to solve for, to find the point or points where are not included on the domain. And remember, since this numerator is just simply x plus 7, which is a standard polynomial, it doesn't really factor into the domain. All right, this numerator will factor into the domain if it's a radical, but since this is a polynomial, even if it says x to the 100th power, it changes how the function looks, but it does not change where how the domain is located. All right, so we can factor this. X minus 7, x minus 4 is not equal to 0. We can use the zero product rule to get two values, x not equal to 7, and x minus 7 not equal to 0, and x minus 4 not equal to 0. So x cannot equal 7, x cannot equal 4 after we solve for those two equations. So on a number line, we'll write in not 7 because 4 is less than that. 4 and 7 are our critical values. And our domain is simply everything that's not those two values. So that would be negative infinity up to 4, union, 4 to 7, union, 7 to infinity. Let's look at another example. Again, x squared minus 49 looks like the difference of perfect squares. Looks like it can factor into x minus 7, x plus 7, but I'm here to tell you once again that does not matter as far as the domain is concerned. Right? Maybe it matters for other things, but not for the domain. So x minus 10 not equal to 0, add 10 to both sides, and x cannot equal 10. So now we have on the number line a domain that's going to be built around a critical value of 10. Let's put 10 at a critical value, and then we can build our OK values, our input values, around that number 10. So everything except for 10 is going to work in g of x right here. And that's the extent that we know on rational functions up until here. Let's start talking first about what is called an asymptote. That is A-S-Y-M-P-T-O-T-E. It's pronounced asymptote. Right, an asymptote is a line that approaches a given curve but does not meet it at any finite distance. Right, and here's what that means, right? When I say a given curve, I'm talking about the graph on an xy axis of this rational function, right? An asymptote is something that occurs in rational functions, right? You can think of it as kind of an invisible barrier because it is not part of the graph, but this line does affect the graph in some case, in some way, where the graph will approach this line, but it will never reach this line at any finite distance. Right, now what this means is that as x gets very large, right, as x, as you kind of draw your finger on a graph from x all the way to infinity, or negative infinity, and that's what I mean by x getting very large or very small. Because remember, we're traveling along values of x. That means this curve will approach this and get closer and closer to this value, this invisible kind of line, but it will never reach it. Right? It's possible that it reaches it at the short run, but not in the long run. So ultimately, what an asymptote is either a vertical or a horizontal line. Right? They can be diagonal, but we're not going to discuss that. we're just going to look at vertical and horizontal asymptotes, which are vertical and horizontal lines, which means that when you identify an asymptote, you must identify it using the equation of a line, right? Either a vertical line, x equals something, or a horizontal line, y equals something. Right, let's start with a vertical asymptote. A vertical asymptote, you can find it by setting the denominator equal to 0 and then solving that resulting equation. Right, this process should look very familiar because this is the exact process, well, not exact, this is the process that we use to find the domain. Right, to find a domain of a rational function, we're taking the denominator and we're setting it not equal to 0, but we are solving it the same way as if it said equals 0. Right, so for here, these vertical asymptotes are going to be located at x equals 4 and x equals 7. Right, so really what you're finding here, when you find the domain of a function, is you're finding where the asymptotes are located. Right, now it is possible that one of these values is not an asymptote, but that is something that I will talk about in class, right? Where this value might not be an asymptote, right? It definitely is not part of the domain, but it doesn't necessarily have to be an asymptote, right? And there's a specific case for that, right? Basically, you should assume that that value is an asymptote unless otherwise noted. So the other type of asymptote is a horizontal asymptote, right? An horizontal asymptote is identified based on the degree of the numerator versus the degree of the denominator. Right, so basically what you're going to be looking at here are the leading terms of the numerator and denominator, right? Think of it as two separate polynomials here, right? X plus 7 is one polynomial, x squared minus 11x plus 28 is another polynomial, right? If you look at this polynomial, this has a degree of 1 on the numerator, and this has a degree of 2 on the denominator. So what you're doing here really is comparing. And in this case, the denominator has a larger degree than the numerator, right? The denominator is larger. And look at here from g of x. X squared on top means a degree of 2. X on bottom means a degree of 1. So now we are looking at a numerator with a degree of 2, denominator degree of 1, numerators is larger. So really when you're comparing these degrees, you can have larger on the numerator, you can have larger on the denominator, or what we haven't seen is that they can be equal. And those are the three types of asymptotes that you're going to get in the horizontal, right? If the numerator has a larger degree than the denominator, then the horizontal asymptote does not exist, right? And this can have a possible slant asymptote, right? It can be diagonal, but again, it's possible, but we're not really going to see much of that. So if the numerator ends up being smaller than the denominator, the degree, again, just the degree, you're not comparing anything else, not even the coefficients, just the degrees. If the numerator's degree is smaller than the denominator, then there is a horizontal asymptote located at the line y equals 0. And if they are equal, meaning the numerator and denominator have the same degree, then you're going to see a horizontal asymptote located at a line of y equals a over c. What is a over c? A is the numerator's leading coefficient, and c is the denominator's leading coefficient. So this ratio, this fraction here, a over c, is going to be the location of that horizontal asymptote if the degrees are the same. An idea is a headache with pictures. So two more things about the rational function is an x-intercept and a y-intercept, right? Same basic locations as regular diagonal lines or parabolas or polynomials. An x-intercept is where this curve crosses the x-axis, and you can identify this by setting f of x, your function, equal to 0 and solving. A y-intercept is the location of, or a point where the graph crosses the y-axis, and this can be obtained by evaluating f of 0. That's plugging in 0 for x and then evaluating. Both of these are going to result in numbers, in answers that are numbers, But since we're talking about x-intercept and y-intercepts here, the answers have to be given as ordered pairs, right? That's something to remember. So let's look at this function here. F of x equals 2x plus 15 over 5 minus x. This is a rational function where we can identify first the domain of this rational function by setting 5 minus x not equal to 0 and solving that. That's subtract 5 from both sides, divide by -1, and then we're going to get x not equal to positive 5. And remember here, we have to build our domain around this value. The next thing we can find here is, I'll call VA, is a vertical asymptote. Remember, a vertical asymptote, the process of finding a vertical asymptote is taking a denominator and setting it equal to 0 and then solving it. Subtract 5 from both sides, divide by -1. Again, the same process as what we did over here, but we're just showing the work again. And that means your vertical asymptote is located at x equals 5. Again, this is the equation of this line, right? And then we can find what's called a horizontal asymptote by comparing the numerator and denominator's degrees, right? The numerator has a leading coefficient, a leading term of 2x. And the denominator, even though it's not the first one there, remember, this is 5 minus x over here in the denominator, but written in standard form, that is going to be -x plus 5. So we have a leading term of -x. Right? This is 2x to the first power and -x to the first power. 1 versus 1 means that these two degrees are equal. Right? These two degrees are equal, which means that a horizontal asymptote is going to be located at a over c. A is equal to 2, and c is equal to -1. So that's y equals 2 over -1, which means y is equal to -2, is the equation of this horizontal asymptote. So remember, we are comparing these degrees in order to find the horizontal asymptote. So now let's look at the x-intercept. Right, the x-intercept means that we can take 2x plus 15 divided by 5 minus x and set it equal to 0. We can solve this by cross-multiplying. We can cross-multiply these. 2x plus 15 times 1, 5 minus x times 0 is equal to 0. So now this is our equation to solve. 2x is equal to -15. That's after we subtract 15 from both sides. We can divide by 2. And we get x equals -15 over 2. So remember, since this is an x-intercept, that means that our answer is going to be an ordered pair where the y-coordinate is always equal to 0. And what's the x point going to be? It's going to be the number that we solved for, in this case, -15 over 2. So this is the ordered pair where the x-intercept is located. So let's look up a y-intercept now. Let's try to find the y-intercept. Remember, our function, it's written over here, so I don't have to scroll all the way back. We are evaluating f of 0. So that's going to be 2 times 0 minus 15 divided by 5 minus 0. We're plugging in 0 for x, and then we're evaluating this, right? So 2 times 0 is 0, and this is going to be -15 over 5, which is equal to -3. But again, since this is a y-intercept, that means the answer is going to be an ordered pair. And on a y-intercept, the x-coordinate is always equal to 0. The y-coordinate is the number that you solved for right here. In this case, that was equal to -3. So here we have, again, let's do a quick review. This is our domain, negative infinity to 5, 5 to infinity. We have a vertical asymptote located at x equals 5. We have a horizontal asymptote located at y equals negative 2. We have an ordered pair of negative 15 over 2 comma 0, which is equal to an ordered pair of 7.5 comma 0 written as a decimal. And then we have 0, negative 3 as the y-intercept. So here I pulled up this graph on Desmos. This is the graph of y equals, I already forgot it, 2x plus 15 over 5 minus x. So let's take a look at some of the components here. We can see over here, I labeled them. This is the y-intercept, 0, comma 3. I got negative 3. Oh, I messed that up. Because this should be a plus. That means that should be a plus. That means this should be a 0, 3, and this should be a 0, 3. Ooh, I'm sorry about that. Alrighty, so now that we got that fixed, we see a y-intercept at 0, 3. We see an x-intercept here at negative 7.5 comma 0. That's negative 15 over 2 comma 0. Right, so each of these grid marks means 1 unit, right? And we have an origin right over here. So if we go 2 spaces down, we see this vertical line, we see this horizontal line, which is x equals negative 2. This should say, oh, I messed that up. Let's erase that. All right, this label, this got messed up. Right, this should say y equals negative 2. And this one here should say x equals 5. All right, so now it's fixed. That's all hunky-dory. So this is y equals negative 2, which represents this, I guess it's red or something like that, dotted line, because it goes through y equals negative 2. And what I'm saying about an asymptote is if you zoom this out, right, which, I can show, if we zoom this out, then you can see that this curve will kind of approach this y equals negative 2 value, but it will never actually reach it. And the same thing over here, right, if you keep on going past this here, right, because again, as x goes to infinity, or x goes to negative infinity, following this cursor, you're going to see this curve, this red curve, is the representation of this graph. You're going to see it approach this value. And as you travel along the right over here, you're going to see this thing go up very, very high. And it's going to get close to x equals 5, but it's never going to hit x equals 5. It's never going to reach that. And same thing down here, right? If you were to kind of take your finger here and move left, this curve, if I were to keep on drawing it, would continue to go down. And it would approach this but never reach it. That's basically what an asymptote is. It's these dotted lines that I have here are invisible. As far as the graph is concerned, they are not part of the graph. Right? These lines, these vertical lines and horizontal lines are not part of the graph. The only part of the curve, I'll draw it in red. The curve is basically this red line, this curve going up here, and this curve going all the way over there. All right, let's actually take a look at this in Desmos. That's going to be 2x plus 15 over 5 minus x, right? So this is going to be, let's say, divided by 2x plus 15 divided by 5 minus x. So you can see the curve here, right? Right, the curve is here, it's in bold and it's in red. If I show the line x equals 5, we can make that a dotted line. That's the vertical asymptote, right? Again, look how close this curve, as I scroll all the way up, look how close this curve is approaching, but never touching. If I zoom in, you can see it's getting really close to it. It's getting extremely close to it. Right, extremely close. It's getting closer and closer, but it's not touching it. Right, if I go down, let's say down to how low can you go? How low is enough? Let's say maybe negative 10,000, right? We can see these x values. You know, we see this curve getting closer and closer. Look, it's actually not touching that line, even though how far away we are. It looks like it. And take a look at this, what this ordered pair is. If I can bring it up. If I can bring up my ordered pair, I can't. Maybe if we look at a table of values or something like that. Right, you can see, let's say x equals 4.5 or something like that, right? Something close to 5. Right, x equals, let's say 4.9. You can see y is equal, the output is 248. And then you can see how large these outputs are getting. 2.5 times 10 to the 12th power is something in the, I don't know, quadrillions or something, as x approaches, gets really close to 5. Oh, I erased it. Let's put it back. Let's say y equals, let's say 2x plus 15 divided by 5 minus x, I think was our curve. Now our curve is in black. And here's our curve. It's in black, right? Again, you can see the x and y intercepts here. You can see that vertical asymptote, which I will now change to say y equals -2. And we'll make this a dotted line again. But notice how this is a separate line because it's not part of the original curve. But there is something happening here. This is the horizontal asymptote. And as x gets very large, as x approaches, you know, infinity, maybe like 160, 165 over here, we can see our curve getting close to that y equals -2 line, but never hitting it, right? Again, all the way out here in the thousands. All right, we can see this line. Is it actually touching? No, it's not. Look how far away it is, right? So that's the basic components of those are the basic components of a rational function. All right, well, I'll put the other one, x equals 5, up here. All right, so we want to be able to identify the horizontal and vertical asymptotes. We want to be able to identify the intercepts as well, right? There's a y-intercept, there's an x-intercept, right? And again, the domain of the function is going to reflect that this vertical asymptote is in place. It's not going to talk, the domain is not going to reflect the horizontal asymptote though, okay? So thank you for watching, and I